Okay, let's go ahead and get started. I'm Charlie Smith, the Executive Director of ESIG. I also serve in a leadership role with the Global Power System Transformation Consortium, or G-PST, whose mission is to bring together key actors to catalyze a rapid, clean energy transition at unprecedented scope and scale. This will be done by providing coordinated and holistic end-to-end support and knowledge infusion to power system operators across the 5 action pillars. The foundation of the G-PST is a group of 6 system operators from around the world who are facing higher penetration of wind and solar inverter-based resources sooner than any other operators in the world. The 5 pillars of the consortium are research and peer learning, technical support, workforce development, technology adoption support, and open data and tools. More information on the G-PST can be found at www.globalpst.org. ESIG serves as a lead of Pillar 1, and as such, would like to welcome you to our monthly G-PST Pillar 1/ESIG webinar series. This series will be in addition to the regular ESIG monthly webinar series and will focus on the research agenda and research questions of Pillar 1. Topics will be presented by both the founding system operators and other advanced system operators active in Pillar 1, and members of industry and academia participating in the activities of the Research Agenda Group and the Research Advisory Committee of Pillar 1. An additional series of webinars on the other 4 pillars of the G-PST will also be provided on a monthly basis through NREL. For those of you who would like to learn more about G-PST and how to engage, please go to www.globalpst.org and click on the Get Involved tab. Further information on ESIG can be found at www.esig.energy. Next, I would like to go over a few logistical matters before we get started. First, all phones will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we're going to be using the Slido platform at slido.com. We'll not be using WebEx for questions. You need to open a browser window, go to slido.com, S-L-I-D-O, and enter ESIG20 as the event code. The instructions are also at the bottom of this screen. You'll see a thumbs up button next to the questions on Slido to allow you to cast a vote to help prioritize the questions submitted. We plan to save 10 or 15 minutes for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions through Slido. Okay, so today our webinar consists of a talk on frequency control in a 100% inverter-based grid. Based on record registrations, it looks like this is a very popular topic. The webinar will feature Deepak Ramasubramanian, a senior engineer scientist at EPRI, who is doing a lot of work in this area. Deepak, in his role at EPRI, is working in the area of modeling, control, and stability analysis of the bulk power system, with recent focus on the associated impacts of large-scale integration of converter interfaced generation and DER. Deepak is one of a limited number of experts in the world in this field. He is not only a nationally recognized, but also an internationally recognized expert in this area, serving for the U.S. on Joint Working Group 5 of Subcommittee 8A on Grid Integration of Renewable Energy of the IEC, a global standards body. I feel very fortunate to have Deepak here with us today. He's a very active participant in both ESIG and the G-PST and a good friend, and it's a pleasure working with him. The webinar today will pose the question of whether there is really a need to make inverter-based resources conform to the slower operational paradigm which reflects synchronous machine operation, or whether the fast response characteristics of an IBR can be leveraged to obtain superior frequency control. When we look back in history on this date, it will be remembered for 2 things. One is the inauguration of Biden and Harris, and the other is Deepak's webinar. Deepak, no pressure or anything. Okay, Just a short reminder once again to use Slido at slido.com with the event code of ESIG20 to ask your questions. And without any further ado, let's go ahead and get started. Deepak, I'll turn it over to you.
Thanks, Charlie. Ryan, I think I might need help again to enable my laser pointer. Yep. Okay. So thanks, Charlie, for that very kind introduction. My name is Deepak Ramasubramanian. I work with the Grid Operations and Planning Group here at EPRI. Forgive me, my PowerPoint clumsiness has put this arrow here on the screen. And what I'll be talking about today is some of the work that we've been doing with respect to frequency control in a 100% inverter-based grid, and also to speak about where do we go in the future with this? What do our standards say? What should we do with respect to, or what can we do with respect to leveraging full flexibility of inverter-based resources and the potential that they bring to the power network? So before we go further, just a recap of some of the theoretical aspects. This is something I'm sure a lot of you already know, but I find that it helps set the tone of the entire topic when we reflect on what is frequency control in a conventional system. And it's good to recollect that in a conventional system, things are inherently linked because of the electromagnetic properties of the network and the machine. So you have rotational speed of the machine, which influences angle because of the electromagnetic link between the network and the machine, which in turn influences change of angle on the load side, which in turn influences speed of motors on the load end, especially if you have induction motors, more so if you have synchronous motors. And all of this has an implicit feedback path that controls or coordinates with each of the elements based upon your Lenz's law and Maxwell's laws that ripple through the network. So if you have a change which occurs on the load end, then that is naturally reflected in the speed of rotation of a machine, and you can govern everything, especially the electrical frequency, by controlling your speed of your rotating machines. So with the fact that all of this is linked, then if we take a look at what happens when you have an event on the system, especially a load generation imbalance event, then you have your frequency which starts falling when you have an imbalance, and you need fast energy injection in order to arrest this decline in frequency. And then as things stabilize, or in order to stabilize the frequency, you need to have some amount of controlled energy injection during this recovery period. And even in a world with synchronous machines, if you have synchronous machines with reduced inertia constants, then you naturally see a faster rate of change or a higher rate of change, but you equally see a higher stabilization or a faster stabilization also, because the time constants involved in the mechanical part of the control system is much smaller due to the smaller inertia constant. So the value of the nadir that you see here, as we see in the rest of the talk, is that it not only depends upon your inertia constant, but the value of the time constants that you have in the mechanical control path or the active power control path, they play an extremely crucial role in deciding how fast you can stabilize your frequency and how you can stay away from the UFLS threshold. So what happens when you have inverter-based resources, and especially the concerns that are there with frequency response, with something which has now started coming up around the world with respect to pockets of systems which have high inverter-based resource penetration. And essentially, one of the major concerns is the triggering of UFLS. So as you have lower inertia constant devices coming into the system, especially if they work in constant power mode, where they are working to inject, let's say, MPPT control or things like that into the network, then in that form of constant power operation, you have a much higher decline of frequency when you have an event, which can then cause UFLS to be triggered much faster before you have other resources which can start responding, because the moment this starts falling fast, then your other inverter-based resources will have lesser time to react to this change in frequency or react to this change in imbalance in the system to start mitigating or to start arresting the frequency response. So this is one of the major concerns that we have with inverter-based resources coming into the network, and it's something that we can hope to address with different control schemes, different control mechanisms with inverter-based resources providing that flexibility. But it's important for us to recognize that this is an aspect which is not necessarily related to only inverter-based resources. So even if you have synchronous machines and you switch off the governor, so you in a sense make the synchronous machine work in a constant power mode, which is what a lot of base load plants operate in, then if you have a higher percentage of base load plants in the system providing frequency response, then there is an equal tendency to start hitting the UFLS threshold. The difference being is these additional 3 seconds here that you gain. So if you have synchronous machines with governors turned off, you gain 3 seconds, as opposed to having the inverter-based resources not providing percentage of the load and not really responding, but at the same time, you still run the risk of hitting UFLS. So the takeaway from this is that the number of resources providing the response matters. So if we have to recap what we have counted up till now, is the number of resources providing response matters, and the time constants involved in the active power control loop also play a very crucial role in order to provide the frequency response in a system. And these are 2 key points that we will revisit as we go later on in the presentation, talking about frequency response in the power network with increased inverter-based resources. A recap with respect to rate of change of frequency is that the primary concern is hitting UFLS, or even a UFLS relay failing to operate or misoperating, because if we look at synchronous machines, the rotating machine by itself has the capability or is designed to tolerate very fast rate of change of frequency, especially because they're also designed to tolerate voltage faults on their terminal. So the main concern is that if we have inverter-based resources, then as long as we can do something with these inverter-based resources to prevent operation of a UFLS relay, then we should be good to go from a frequency response perspective. This doesn't imply that legacy protection thresholds or protection settings may not be impacted. That's something for us to tackle as we go along and as we learn from operation of the power system. But the major concern is as long as we can mitigate the rate of change of frequency falling and hitting the UFLS threshold with inverter-based resources, then it's something which we can satisfy a good frequency response. So up till now, it was just a recap. This is something which is probably common knowledge for a lot of you folks on the call, but helps set the tone of where we are going with this presentation and where we are going with this talk. So let's move on to a situation now that if you have increase in penetration of inverter-based resources and start touching upon frequency control from the perspective of inverter-based resources. So inverter-based resources around the world continue to increase. This is just a snapshot from North America. It's not a very up-to-date snapshot. There are, I think, in the recent past, there have been few more percentages that have been hit. But system operators around the world, regions around the world are inching towards the 70%, 80% mark. There can be situations where pockets of a system hit 100% instantaneous penetration in energy delivered from inverter-based resources for a few hours of the day. And that is the kind of situation that we want to try to immediately address with respect to frequency control, because if an event occurs in the system at that point in time, then that's something for us to be ready for, that's something for us to be prepared for as we start hitting these percentages more often in the system nowadays. But as we are going towards that, we also need to start talking about standardization. We need to start talking about what are the present standards saying with respect to frequency control? Is there something going on in the standard development scenario, in the standard development arena, which is already addressing this, is something for us to look at with respect to this frequency. So presently, there is in IEEE, there is a draft standard which is being formulated, which is being termed as 2800. What this draft standard is meant to do is it builds upon, or it takes lessons learned from IEEE 1547, which was for distribution connected inverter-based resources, and using that as a starting point, it has been drafted in order to cater to bulk power system connected inverter-based resources. Now, presently, the status of the standard is it's in a draft form. It's going to go out for public balloting, a public comment period soon. And once we get back responses, or once we get back comments and feedback, then we will take that into consideration and the drafting process will go further. So if you're looking to get involved in the standard, please feel free to send us an email and we'll be happy to let you know how you can get involved. Now, with respect to this draft standard, the draft standard tackles voltage write-through, tackles voltage control, it tackles other aspects related to model validation and things like that. But it also tackles things like frequency response. And especially, let's take a look for now only at primary frequency control. So primary frequency response as we know it today, the draft P2800 standard speaks about this primary frequency control in the following manner, that supposing you have a change in the system quantity of, let's say, a step response kind of a change, and you have a change in the system quantity being, let's say, frequency here, then the minimum expectation from an inverter-based resource is that the response from an inverter-based resource will follow a trajectory which is governed by these minimum values. So it will have a minimum reaction time of 0.2 seconds, a minimum rise time of 2 seconds, and a minimum settling time of 10 seconds, with a minimum value of damping ratio and settling band. Now, note that these are minimum capability that is expected to be met. If the IBR plant can technically go above and beyond, it's expected to go above and beyond, but the minimum capability is specified here in this draft standard. And also in terms of the rate at which the IBR plant will increase its output, while a particular percentage or a ramp rate setting is not specified, what is said is that the change in output should not be greater than the maximum ramp rate of the plant, while it is being as fast as technically feasible. So for some resources, this value may be a certain value. For some other resources, based upon different constraints, might be a slower value. But it's dependent upon the resource that is providing this response. And that's something which is very important, which we will see next. And the standard values with respect to deadband being 15 to 36 millihertz and a 2 to 5% droop. So the question we asked from our end at EPRI is that, will this capability ever be sufficient for a 100% inverter-based grid? Now, note that we're not asking, will it always be sufficient? We're asking, will it ever be sufficient? Are there instances where it will be sufficient? And are those instances important to be considered and understood? And what do they tell about the type of response that will be delivered? What are the key features that one needs to take into account with respect to these plants' response as we continue to evolve in IBR controls, as we continue to go towards advanced IBR controls? What are the things that we need to be looking for is something that we wanted to take a look at. So looking at this question of, will this capability ever be sufficient? Let's take a look at what happens if you have a network which is an existing strong network. There's a very strong infinite bus here, and you have two PV plants connected in that strong network. So you have these two PV plants, and what we do is to try to represent or try to mimic the kind of a way of evaluating the response of a plant as specified in the draft standard, we introduce a step change in the frequency of this infinite source. So it's something it's a step decrease in the frequency which is appearing on the system end. And we want to see how these IBR plants with all their control systems, they have these two PV plants, they are designed in such a way that they have 17 millihertz deadband and a 5% droop at the inverter level. And we want to compare that for this reduction in this frequency at the infinite bus, how would the response of the control of the plant change when observed at its terminal for two different ramp rates of 1 per unit per second and 10 per unit per second. So these are ramp rates that are set on the active power command of the plant. Now note that these plants are very conventional kind of plants, so they have to measure the frequency, they need to sense what is happening with respect to the frequency, they need to filter it, they need to act upon that measurement, and only finally can they then change their active power command that's given to their inverter, and then they have to act upon it in terms of the current control and things like that. So all of the full-blown details of the control which is used in this plant is actually available at this link here for folks who want to take a deeper dive into it. And we see that for two different ramp rate values based upon the 1 per unit per second and the 10 per unit per second, there is a noticeable change in terms of the fact that the 1 per unit per second, you can see it being clamped to 1 per unit per second here in the red curve with respect to the reference command, whereas the orange curve with respect to the 10 per unit per second, the reference command has a more noticeable exponential kind of a response. And there is a minimal difference between the final active power output that you see at this terminal here at the bus here. Now, from a draft P2800 standard perspective, both these ramp rates, they meet the requirements of the plant, right? They meet what is happening, they satisfy the draft standard, and one wouldn't think too much about this difference in the response here because they seem to be pretty close to each other. So one might think that, okay, this is not something which is important enough, or it's not something which is crucial enough to be considered, because we have a tendency to ignore such ramp rates when we are talking about things like fast injection of current into the network or frequency-based disturbances. But remember, this is a response in a strong network. The moment you put this in a weak network, and we went to the bookend minimum or bookend weak network perspective, where what we did was we just disabled the infinite bus. So everything now becomes a 100% IBR network for the same system that you saw on the previous slide. All that was done is disable the infinite bus at 2 seconds. And you see that now in the strong network, although 1 per unit per second seemed to be a reasonable response, it's unstable, or it's unable to take that transition when you go to a weak network. And rather it's the 10 per unit per second, and here even 5 per unit per second provides a reasonable response, or provides a good settling point, provides a good steady state frequency, and subsequent load increase that happens in the 100% IBR network, it's able to even tolerate that, and it's able to provide a response which is satisfactory. So laying very crucial emphasis on the fact that what might seem as a good ramp rate when we look at it from a strong network perspective might actually not be a good ramp rate when you look at it from the perspective of as the system strength increases and as you want these inverter-based resources to provide faster response. What one also needs to be concerned about is that these ramp rates are actually influenced by the source behind the inverter, which means that a battery energy storage system could tolerate a higher ramp rate as opposed to wind turbines, which will have mechanical components which may need a lower ramp rate, or which can only tolerate a lower ramp rate. And if we are going to evolve into the system where we want inverter-based resources to provide services in terms of arresting frequency decline and helping the frequency nudges stay away from the UFLS, then we need to pay a lot of attention to this ramp rate value that goes into play in these resources, because they can have a large potential impact on the system. Now, this is with just 2 resources, and one might say that, okay, but what happens if there are wind resources which are the majority of the fleet, or what happens if there are resources which cannot move fast and they have to have a lower ramp rate. That's where we come back to that initial point that we spoke about, that more number of resources or the number of responsive resources plays a very crucial role. So if we go back to that same network where we created the 100% inverter-based scenario, then if you have to go down to a 2 per unit per second ramp rate, then in this case, we needed 3 plants of 100 MVA each, rather than having the 2 plants of 200 MVA each for the 5 per unit per second scenario. So the lower the ramp rate constraint the resources are constrained by, the more number of resources one will need to provide this kind of a frequency response service in a 100% inverter-based scenario perspective. And what that means is that the sharing of the energy burden now needs to be socialized across a number of resources. But supposing you already have a large number of legacy devices that are inherently limited by these ramp rate constraints or are not designed to provide these kind of frequency response services, then it's important to recognize that as you have more number of newer inverter-based resources coming into the system, they would have to take up an additional burden of what the older resources would have to provide, which means that if you had traditional inverter-based resources, so let's say 2 per unit per second, but they cannot provide a frequency response service in a system with increased inverter-based penetration, then the newer inverter-based resource that's coming in should not be at 2 per unit per second, but rather it might have to be at 5 per unit per second or even 10 per unit per second, so that it can take on that additional burden. And what that means for the energy source behind the inverter needs to be considered. And that's something which is very important for us to consider as we start planning for inverter-based resources providing frequency control in a 100% inverter-based resource system, that things like the constraints imposed by the source behind the inverter, especially with respect to the ramp rate constraint, is something which is very important for us to consider. And this can happen with any form of IBR control. We're not trying to single out any one particular form of IBR control here, because at the end of the day, it's not the IBR control that dictates this ramp rate, but it's the source behind the inverter that dictates this. So any form of IBR control that we envision will inherently have some form of ramp rate limitation that will have to be overcome as we are planning the system. So just to have an interim summary of what we have here is that the increased rate of change of frequency, the way we have it, can cause misoperation of UFLS relays. It may also cause UFLS relay to be hit, but the draft P2800 standard has potential to provide tremendous benefit the way it is right now from a frequency response perspective. But we need to be cognizant of things like ramp rate and the dynamics of the source behind the inverter, and also the number of resources that we're calling upon to provide this service, while keeping in mind that we have to ensure that the inverter-based resource is providing the service as fast as technically feasible without causing any instability. So it doesn't mean that you have to have a fast ramp rate if there is a subsequent instability that occurs. That needs to be considered. So once we have this, let's move on. Okay, what are the obstacles that are there for inverters to provide this kind of responsive service? And this is again something which a lot of you folks might already be aware of. It's not something new, or it's not something which is aha, which we're talking about. Generally, things like if you have to measure frequency, you have to measure it robustly. There's time taken to get that robust measurement, which may influence the response that you have. You need to have robust controllers. You need to have robust measurement techniques itself, and you can even get responses without even measuring frequency, which are available. But all of this boils down to the different types of control within the inverter, which may still be limited by the source behind the inverter. But if we have all that, let's go beyond, right? We know that inverters have very small time constants, especially if you're talking about a battery energy-based system or a PV-based system that do not have mechanical time constants. Then you have the flexibility to draw upon this very fast resource in terms of how it will provide the service to the system. So let's try going beyond. Let's envision a scenario where the operation paradigm of the system goes beyond just frequency droop. And that's some of the research that we're doing here at EPRI to see what will be the implications of that and can we even achieve that. So if we go back to our initial cartoon that we showed in the few slides of the presentation, then we have everything staying the same on the load side. We have everything staying the same on the network side. But what changes is the electromagnetic link that was there on the source side. So you no longer now have the electromagnetic link between the source and the network, which potentially means that any change that occurs on the load side need not necessarily travel back to the converter, because that physical link is broken down. And if that physical link is broken down, it means that we need to now decide how we want to control this converter, because it can do anything that we want it to do, and they can operate at any frequency. So with this kind of a scenario, if we have to leverage this superior frequency control that we can get from an inverter, we ask the question that, can we get the ideal L-shaped frequency response? So for those who are not aware, an ideal L-shaped frequency response is a scenario where if you have an event on the system, you don't have a frequency nadir and you don't have a frequency recovery period. Rather, what you have is a frequency trajectory of the system that almost instantaneously goes down and settles at a newer value in almost a step fashion. And that ideal L-shaped frequency response has minimal dynamic characteristics involved in it, because it's almost like an instantaneous flip of a switch that the frequency goes down and settles at that lower value. And can we do better than that with inverter-based resources is something that we wanted to look at from a frequency control perspective with our research work here at EPRI. But this raises a philosophical question that just because it can be done, should it be done? So we are at the crossroads here that we want to leverage flexibility of inverters. We want to leverage superior control, but we also need to take a pause and question ourselves that should it really be done? Does the system really need it? And it helps to think about these particular scenarios that traditional needs of frequency control breaks down about motor drives, but motor drives are transitioning to power electronics. Then we have clocks that may run on frequency of the system. We have magnetics. We have machine torsional stress. If you have something like a 90% inverter-based resource system or an 80% inverter-based resource system, then there's torsional stress that can come out about machines. But at the same time, we have these static generators, which have very low time constants. We have the control capability available. We have smart transformers coming into the picture, where they're power electronics-based transformers. We have power control devices coming into the system, like non-wire alternatives and things that can go on transmission lines. And we have increased observability in the system. So you have next generation monitoring and control that can potentially be leveraged. So we don't have an answer to this question yet, but there are these pros and cons that as the characteristics of each of these devices that need frequency control, that if once those characteristics change, we slowly start transitioning more onto this end of the system, where a lot of elements are power electronics controlled or power electronics interface, which means that we can get superior flexibility and we can actually do this kind of a superior control system. So what does that look like? And that's something which we worked at. Is it works something like this. We envision a concept where you take your traditional concepts of distributed slack bus, which is very common from a power flow perspective. It's very common in the real world, where a slack bus exists only in mathematical computation of your power flow problem. It doesn't exist in the real world because usually it is socialized across a lot of machines. And we use that concept of slack bus to designate a newer form of power sharing that can work even in the dynamic domain. And what this does is this can get us better than an ideal L-shaped response. So consider this case where you have all synchronous machines and you have your very familiar frequency droop characteristic that you obtain. But if you have the same system with the same headroom available and you have all inverter-based resources, then you can potentially get this form of a frequency response across a very wide network. This is not restricted to small island systems. Across a very wide network, you can potentially get this form of a frequency response characteristic, where the frequency goes back to nominal within few seconds of having a load disturbance change. Now, it doesn't mean that this will always be stable. As you can see on the graph here on the side, that there are certain components of it that have an unstable trajectory, but if adequately tuned, if adequately parameterized, you can get this kind of a response. And this is something, just to put a note here, this is over a very large system, looking at it from an interconnection-wide perspective. This is boiling it down to a smaller local area just to see what happens with respect to this frequency response perspective. So once you can leverage this flexibility of these inverter-based resources, we can potentially do away, or we can not hold on to frequency group control, and we can go with this advanced form of frequency control in a 100% inverter-based resource scenario, where we can come back to frequency being nominal within a few seconds of the disturbance. And this is at a very low increased energy burden. So for this scenario that we are studying here, it was an increased energy delivery of 10 kilowatt hour. At that low increased energy burden, you can go from the orange curve to the blue curve when you have multiple devices providing this kind of frequency response over a very wide. And it relates, and it comes back to a scenario that we also spoke about before, that we should not be focusing on specific inverter control types, and we should not be looking at because any inverter control type will be limited by the source behind it, and different types of resources can provide a similar kind of response. So going back to our scenario where we had 100% inverter-based resource network that was connected or that was formed, and if you have a load increase and a decrease event, then based upon the type of resource that you have, based upon the type of frequency control that you have. So the constant frequency control is what I showed just in the previous slide, where you have distributed slack burst-based response. Your droop curve is what you have presently in our group-based systems today. Virtual oscillator is a new form of inverter-based control that is coming up, which provides a different kind of response. But overall, from a system operator perspective, from a system operation perspective, all three of responses are acceptable. There are differences, yes, there are nuances involved, but all three responses are acceptable from a system operator perspective, which just means that you can leverage a wide variety of frequency response solutions or frequency control solutions as we go towards a 100% inverter-based resource system. And the focus should be on performance capability, which is what standards like P2800 are trying to address. That if you focus on performance capability rather than control methodology, then one can move towards a system where one can get a standardized response from inverter-based resources, which is easy to work with and easy to model and easy to control across the entire network, while still allowing for technology innovation, while still allowing for innovation in different forms of inverter-based control. Now, all of this was from a perspective of EMT domain, perspective of going into the weeds, into the types of control with respect to inverters. But a question that keeps coming up in our research work is, can positive sequence models, which are used for inverter-based resource studies, or which are used for interconnection-wide studies, can such models be used? Do they still hold relevance as we move to a 100% inverter-based system? Or should everything become an EMT domain and there is no use for these kind of models at all? So there are presently few generic positive sequence models that are used in the industry. I have to be careful here that generic means that it can be used to represent the characteristics of different inverter vendors. It doesn't mean that the same parameter values are used across these models. The parameterization of these models needs to be different based upon the situation that it's being used for, but it is generic enough to not hold proprietary information of any particular vendor control and can be used across a wide variety of devices. So we looked back at the system where we have virtual oscillator control and EMT domain, and we have few StatComs in this 100% inverter-based resource network, and we compare the performance of these generic models as they exist in software today. So software like PSSE, software like PSLF, PowerWorld, Power Factory, they have these generic models available. And we wanted to see that can you simulate a 100% inverter-based resource network and look at the frequency response characteristics using these models in such a simulation software and compare it with these advanced controls in EMT domain. So this is just to show how we will model these resources. As you see here, these are the generic model names, and feel free to reach out to me if there is any questions regarding these generic models. It's too exhaustive to talk about in this webinar, but I will most happy to talk about it later on for folks who are interested. And what we did was, because a virtual oscillator control in some way mimics an isochronous control mode, we went beyond our frequency group control that we spoke about earlier. We went beyond that frequency group control and implemented a distributed slack bus type of control to kind of see how these controllers will interact with each other and can they provide the kind of frequency response that one may observe from a virtual oscillator framework. And this is the response that we got from the two models. So in EMT domain, the blue curve shows for a load increase and load decrease with you having the virtual oscillator control and with having the 100% inverter-based resource network. The orange curve is the same system, but in positive sequence domain with the generic models that are available today in PSSE or PSLF, and for the same kind of a load change. Note that the models have to be appropriately parameterized, but we find that potentially they can provide a semblance of the response one can see from these detailed EMT simulations. This is not to say that they can replace EMT simulations, or neither is it to say that you can completely do away with such models or generic models will be the only models that need to be used. All this is trying to say is that the capability exists in the toolboxes available, and we can use that capability as a starting point to start studies that can then evolve as the system evolves. But with this kind of constant frequency control, or with this kind of distributed slack bus perspective, where frequency becomes back to nominal value within a few seconds of disturbance, a legitimate question to ask is, what would balancing authorities do? Because our present concepts of secondary frequency control that we have is very much dependent upon frequency deviation and frequency settling at an off-nominal value, along with change of flow along tie lines between two areas, which is then used to bring the frequency back to nominal and then let each control area or each balancing area take upon its disturbance. So we took upon the study where we implemented our constant frequency control across multiple areas of the network, and we found that just by looking at tie line flow, you can still get the same form of secondary frequency control properties with frequency already being at nominal. So you just remove the frequency portion of your area control error calculation, and you can still get the same kind of response across wide areas also. It does raise the question of what will be the impact of, let's say, SCADA or EMS refresh rates, because if the frequency is already back to nominal, will a system operator know that there has been an event on the system? That's something to address. Also, what will be the impact on things like the CPS scores that are usually evaluated for balancing areas to evaluate whether the balancing areas are taking up their respective burden with respect to generation load imbalances. So these are open research questions with respect to this advanced frequency control in a 100% inverter-based resource system that our research is trying to address as we go along. And we have to talk about larger networks. It's all good and to talk about the IEEE 14-bus network and show this working there, but the legitimate question comes is, okay, will this really work on large systems, or is this only restricted to smaller networks? Is this only something that works on a smaller scale? So once we go to larger networks, a whole different set of problems can come up with respect to frequency control, with respect to inverter-based resources, which is something that we were looking at, that the location where you have to get frequency control from or frequency response from can be very important. Take the scenario where granted you can get a better frequency response or a faster frequency response when you have 88% of the fleet being inverter-based resources, but in case one here is where the frequency response is coming from an electrically far away region, and case two is where it's coming from an electrically close by region. So there's one thing that the devices from an electrically far away region have to provide much more response, which means that you have to plan for that capacity being available, you need to plan for that level of headroom being available if they have to come up from that electrically far away resources. The other thing is with respect to stability, that if you're trying to push power from an electrically far away region, then it's going to come into different stability constraints with respect to frequency response. Now, one can say that it's intuitive that yes, you need frequency response in the region where the disturbance is, because closer the frequency response, it's an intuitive result to get a better response available. But it's not so intuitive when you're planning for the future system, that you don't know where the disturbance is likely to arise. You don't know where your single largest contingency might be as the system evolves. So how do you plan for these resources coming in? How do you allocate where you want your frequency response services to come into play is something which is very important to consider with respect to the locational aspect of getting frequency control in 100% inverter-based resource system. This thing works, but however, if it is adequately planned, if it is adequately situated, it works on very large networks. So we looked at it for the WEC network, which is the Western United States, the network, the interconnection which is here in the Western United States. And this is for 100% WEC network. The WEC network has a capacity of around peak load of around 160 gigawatts. And for that 160 gigawatt network, for 10% or not 10%, 4% load increase that occurred, which is their regular planning criteria, assuming all inverter-based resources are sufficient headroom, then you can get numerically robust results and you can get a scenario where you have stable frequency response across the network if the inverter-based resource controls are tuned or designed or located in adequate location. Frequency control also helps push more power from an IBR along the corridor. This is in a way a sneak peek to something that is coming in the next ESIG webinars, where they'll be talking about how to push power or what needs to be thought about, what we need to do to help push more power from inverter-based resources across a certain corridor. And there also having some form of robust frequency control can help. So this was a study that we did in a local region of South Texas that had N-1 issues for 70%, or if the wind penetration went more than 70% in that region. And by allowing for robust frequency control and voltage control, we could push that power out and increase the power export by 1 gigawatt in that region. There are considerations involved with respect to the sizing of the converters, of course, but that is an electrical problem that was observed even if you replace these inverters with rotating machines. But it has nothing to do with the, it's nothing unique to inverter-based resources. It's a response that you would get even with rotating machines. But with having these kind of robust frequency control, you can help push more power across the large corridors and export more inverter-based resource power. So to summarize what we spoke about today, is that what our work has shown is that it's possible to take advantage of the flexibility from inverter-based resources, and the present draft standards that are being developed, they can have potentially tremendous benefit as long as we keep in mind certain key points, especially with respect to how the ramp rate is and how the speed of the response of these devices naturally is, as far as they're providing response as fast as technically feasible. We can also go beyond traditional frequency group control because we can leverage the flexibility that these inverter-based resources provide, and this can be achieved even across wide balancing areas, where you can ensure that each balancing area is picking up its own burden of the generation imbalance. But we need to be cognizant that as we are moving towards this kind of newer paradigm, we need to focus on specifying performance-based requirements rather than inverter control methods, because that could end up being a limitation. And some initial research has shown is that we may already have models available to study this kind of scenario. It's by no means a model which is the end point of modeling, there are always newer models that can be developed and need to be developed, but we are probably also not in the dark. We do have some models available in our traditional software. So for system operators and planners out there, models that are available in the software that you use regularly day in and day out, you might have models already available there to start studying these kind of systems, and they can be leveraged. And finally, the location with which you provide this frequency response can end up becoming very crucial as our system moves towards 100% inverter-based resource. So Charlie, with that, that's my end. I'll keep up this slide, which speaks about a further reading. It's not an exhaustive list by any means. And then happy to take any questions that have come up.
Okay, we've got a lot of questions there, Deepak. Thanks for that walk through IBRs and frequency response. There's a couple of the first ones here related to assumptions. Are you assuming that the PV plants have available headroom to increase their output to respond to the under-frequency event? Was asked about halfway through.
Most definitely, because in a way it becomes a moot point if you are studying 100% inverter-based resource network and all the inverters in that system do not have headroom. That becomes a moot point. So yes, definitely we assume there was headroom, but we have looked at what will be the impact of the percentage of headroom that is available. So if you have lesser number of resources, lesser amount of headroom, how the frequency trajectory will change.
Okay. Another question on assumptions. How do you specify or define a strong system versus a weak system in your studies?
Yeah, in all our studies, there is no clear-cut definition of what is strong versus what is weak, because it completely depends upon the characteristics of the system that is being studied and the nature of the devices which are operating in that system. So for example, if one looks at it from the perspective of weak system being defined by long transmission lines, then definitely the 100%, the IEEE 14-bus network with 100% inverters wouldn't be considered weak because there is no physical long transmission line. At the same time, it can be considered weak because there is limited short circuit contribution in that system. So there is an apparent long transmission line between each devices. So in that way, the definition of strong versus weak is very fluid in our studies and in our simulations.
Okay, here's an interesting what-if question. To what extent would adding physical inertia, for example, synchronous flywheels, improve the stability and robustness of a grid with 100% inverter-based frequency control?
Yeah, so Steve, definitely there will be an implicit improvement, but there is no guaranteed improvement. So one of the last slides that I showed, which showed about increasing the transfer of power across the corridor in South Texas, we did a comparative study between seeing what will happen if it was inverter-based resources versus synchronous machines. And there were certain situations where with synchronous machines, you could get an unstable response if the associated elements like the power system stabilizer and the excitation system were not tuned properly. And the same thing can happen with flywheels also, that adding that physical inertia, there could be a conflict between leveraging the flexibility and the fast-moving nature of an inverter-based resource and contrasting it with the inertia from a flywheel. There could be an oscillatory mode that develops across them, which needs to be studied and understood while implementing these kind of resources. Good
question. Here's an interesting one. What happens in a 100% IBR grid when there's a mismatch between mechanical and electrical power, since frequency is determined by PWM control?
That goes back to the initial question itself: is what is frequency in a 100% IBR grid? Our notion of frequency is governed by mechanical speed, and the deviation of frequency is the mismatch. What will happen is that when I assume you said dispatch between mechanical and electrical power, I'm assuming you're talking about a wind turbine where there is the mechanical and electrical power. What will happen is that if it's a type 4 wind turbine and there is a severe mismatch between the mechanical side and the electrical side, especially if the controls are not coordinated across the DC bus of the inverter, then you will see a distinct drop in DC voltage or a distinct rise in DC voltage depending upon what paradigm is being played out. And that can cause equipment to trip out because the DC bus voltage will be sensitive. And it's actually something to be considered while you're looking at how much capacity of frequency response needs to be provided and needs to be transferred across the DC bus of these inverters.
Okay, Deepak, Kwame's been waiting since December 23rd to ask his question. So, how ready is the energy industry for 100% inverter-based resource penetration scenarios? Kind of a philosophical question, I guess.
Yeah, it works two ways. How ready is one question. The other question is, do we have a choice? Because there are certain, or do we have to be ready come what may? Because there are certain regions which are already inching towards 80%, 90% instantaneous penetration. What I would say is that there are different aspects that need to be considered. There is definitely the aspect of whether the economic aspects of 100% inverter-based resource system that needs to follow up with respect to the technology aspect. So while we might have technology available, we may not have the economic or the markets aspect to be built upon that, which is a very fluid scenario. So I don't think there's a clear-cut answer of whether the industry is ready or not. I think there are many interrelated questions that need to be answered with respect to how they would work together.
Okay, here's a couple of DER questions. I know that DER wasn't the focus of this, but maybe you could entertain them. Many DERs are interconnected at low or medium voltage level, assuming they have a resistive output impedance. What droop curves are they supposed to use, QF or PF? And then a related question, for coordinated inverters on the distribution system, is it better to socialize their frequency responses or manage as a single IBR?
Yeah. So for the first question with respect to what kind of droop curves are they supposed to use, it depends whether they are also connected on what voltage level are they connected at, how are they going to provide that kind of response, what type of DER they are, if they are a utility scale plant which is connected closer to the substation, or if it is a residential rooftop PV that is connected, all of that will dictate what kind of droop curves they use. Now, as with respect to the present 1547 standard, there are both a capability for something called frequency watt and volt watt kind of functionality. So you can have change in active power with respect to voltage and change in active power with respect to frequency. And depending upon where the DER is being connected, they will have to decide which kind of droop control is being used, which is beneficial for that system. So long story short, I don't think there's a generalized answer of what curve they're supposed to use, but the capability should be there to use either or, depending upon where those inverters are connected or which part of the system they are connected to. Now, with respect to the second question, Charlie, about also citing FERC Order 2222 and better to socialize, I don't know if there is if it's an answer which can be spoken about which is better. There is definitely the aspect that if they are going to be managed as a single IBR with respect to taking a look at their local measurements and responding, then they need to have proper droop constants across their network so that they don't fight with each other. If they are coordinated in a manner like, say, for FERC 2222 and they are operating as a single entity, then there are the other aspects to consider with respect to communication, with respect to how will they optimize their response as a group. Will that optimized response be fast enough for the system? Those are things that need to be considered when deciding which response is better as compared to the other.
Okay, I'm going to take one more question, Deepak, from Mark O'Malley. As others have indicated, you need headroom, i.e. stored energy. How does the stored energy compare to rotational energy, in particular equivalent performance? So I think, how much stored energy do you need compared to rotational energy to get equivalent performance out of the system, I think is the question.
Yeah, definitely. So Mark, one thing is when you have a frequency event on the system, you don't use up the entire rotational energy that is there in a rotor. So if we consider a inertia constant of, let's say, 3 seconds of a thermal power plant, and that's a 500 megawatt power plant, essentially it takes 3 seconds to go from 500 megawatt to 0 megawatt. That's how you define inertia constant. And we never usually use up that entire rotational energy. So the amount of rotational energy, the amount of headroom or stored energy that might be required depends completely upon how much frequency deviation we are willing to tolerate. And we definitely won't need the entire amount of energy as compared to what you have as a rotating energy in the machine, because we never use that up anyway. So I don't have a specific number or an answer in terms of percentage, but I think that's something to keep in mind, that as we define amount of energy required, it may not be an apples to apples comparison saying we need X GVA of energy because we had this much in a rotational machine. But it's important to consider that if you had a frequency deviation and within 59.5 of your UFLS threshold, how much of that energy did you actually consume from a rotating machine? And that's the amount of energy that you will need for your response systems.
Yeah, it's an interesting way to look at it. Okay, we're just past the top of the hour, so I think we're going to need to wrap it up. Deepak, thank you for a very educational presentation. I think we all learned a lot from it. As I mentioned earlier, an email will go out once the video file has been posted. I want to encourage everyone to send any follow-up questions you have to info@esig.energy, and we'll get them answered and posted as quickly as possible. We appreciate your engagement. We look forward to seeing you at our next webinar in this series, which will be held on February 10th at 4 p.m. Eastern. And Christian Schaefer of the Australian Energy Market Operator will be speaking on their work on developing an engineering framework to support Australia's energy transition, which I think should be a very interesting one. And we hope you'll be able to join us for that. Further information on all of the webinars can be found on our website at esig.energy under events, and you're all invited to attend. And information on all the G-PST webinars can also be found at globalpst.org. Deepak, I want to thank you once again for this very timely, fascinating webinar, and thank all of you on the call for your interest. We look forward to seeing you again in February. In the meantime, everyone, take care, stay safe, and thanks again for your participation. Bye now.